Alrighty. Today I'm going to be doing another problem from the FAU lecture. If anyone's following along, this is just the second problem that the professor did. I'm going to walk through it and describe it as I go along. I'm, again, not an educational professional. I don't have a PhD in this, and I'm not credentialed. So, this is really for my benefit more than it is for your benefit. If it helps you out, great. If not, then that's all right too. So here we go. So let's open up a new page. And let's call this PID exercise 2. So let's open up the PowerPoint. This is the problem that we're going to be doing today. I'm going to go snip this problem. All right, there we go. All right, so problem. First thing I always do is I do givens/assumptions. Helps direct my thoughts and, kind of helps me read the problem too. We'll start with givens/assumptions. So reading the problem says consider a proportional integral control of the first order. Okay, so it's a first order system. And exercise number 1, so we're piggybacking to the first block diagram that was in the PowerPoint. So for those of you who are just now watching, it's this block diagram we're dealing with. So I will take that and I will drop it in here. Well, hold up before I do that. Well, I'll read a little bit more into it before I drop the block diagram into the page. So it says consider a proportional integral control. It says integral control. That block diagram displays only a proportional control. So this one has a PI, which is equal to KP, K sub P, plus K sub I all over S. So that's the big difference. So let me drop that in. Actually, no, I have to manipulate it. Did that by erasing this. Okay. So I set that in the background. So this expression, the PI expression, it's going to go into this control block. So I want it to look professional, so I'm going to go ahead and do the ink to math. It'll let me. Why isn't it letting me? I'll do this. All right, well, that's not working out for me, but that's all right because I have it on my other notes. So I'm just going to copy and paste it. That is on my other screen. So this is what needs to go inside here. Could be a little smaller. I'll make it smaller. All right, there it is. So that's that control block. Says the dominant time constant is specified to be 0.5 seconds. So they give us a time constant, tau, 0.5 seconds, and the dampening ratio to be specified to be 0.707. So there is our dampening ratio, zeta, 0.707. Now the task, the finds, the things we're looking for. It says compute the required values for Kp and Ki. Okay, so A just wants K sub P equals question mark, and it wants K sub I equal question mark. And then the second part says evaluate the steady state command error and steady state disturbance error given that both the command speed and the disturbance torque are unit step functions. So it's really part B is really two parts. So it's really part B is finding your steady state command error, and C is finding your steady state disturbance error. So we know what we need to look for, and we've taken all of our givens. So the first thing we need to do is to find a closed loop transfer function of this block diagram. All right, so do it the hard way, the way in which I prefer. For those of you people that are a little wittier than I am, you don't need to follow along on this part. I just do it the longer way just because I'm pretty visual. You know, I need to kind of see everything as it goes along as it's happening. I need to see it. So that's just me, to each his own. So writing out the error function. And like before, if anyone watched, I don't like these capital omega sub r's and omega s. I'm going to call this capital Y sub r of s and capital Y of s, just because it's easier for me to kind of look at as I'm doing my math. So E of s is equal to capital Y sub r of s minus Y of s. There's one piece of it, and T of s is equal to capital E of s multiplied by Kp plus K sub I all over s. And then we have capital Y of s. And that will give us, well, let's think about this piece here. What is this piece of the block diagram? It's simply just a summation of that junction, which is just going to be T, capital T of s, minus the disturbance, which is T sub D of s. Which will give us this expression here of the capital Y of s. It's going to be 5s plus 2. So we have all these expressions now. Now we can find the closed loop transfer function, which the closed loop transfer function, just to, you know, make everyone aware, is going to be H sub C of s equal to capital Y of s, which is our output, capital Y sub R of s, which is our input. So the transfer function to any type of system is output over input, which kind of makes sense though, because you kind of know what you're putting into a system, but we don't know what we're getting out of the system. So that's something that we need to know. I'll highlight it. And now I'm going to back substitute that error equation into the T of S equation. And obviously here's the rest of it. Now we can obviously FOIL this out. It might be a good ideal to do that. And because I like to kind of be very, very detailed. Some people forget how to FOIL, and that's okay. And foiling is this. Bam, bam, and this. And you'll kind of get what I'm doing in a second. Most of you guys can do this in your head. I'd rather not do it in my head. I can, but I'd rather not. So I'm going to have capital Y R of S times KP plus capital Y of R of S K sub I over S. Now we're minus Y of S times KP minus capital Y of S K sub I all over S. Now looking at this, can we make this a little easier to look at? Well, I could factor I guess I could do this. Actually, I should factor out that negative, just for consistency's sake. And I actually think, yeah, that was a good choice. Factoring out that capital Y sub R of S and that capital Y of S. That was a good idea. So the next thing we're going to do is we're going to back substitute that capital T of S into the Y of S equation and see what we get. So we'll do that now. Capital Y of S will equal capital Y of R of S Kp plus K sub I of S. And I'm just going to go ahead and put the 5S plus 2 in its denominator. If that kind of is a little too fast for you, well, that is what it is. Capital Y of S, Kp plus K sub I of S all over 5S plus 2. And last but not least, minus Td of S all over 5S plus 2. All right. So this is that expression that kind of has everything. We can use this to get the transfer function for our control. And we can also get this transfer function for our disturbance. So this is everything. Very nice. All right. So for the first part, and what is the first part? It's asking for Kp and Ki. Kp and Ki. Okay. So we need to create our in standard form our transfer function for the command control error. So I'm going to copy this expression here, copy it, bring this guy back down. And what you see here is that this, because we're only considering the command, we're not considering disturbance, so we're going to neglect the disturbance. It is now 0. It goes away. So with that, we can now get that capital Y of S over capital Y sub R of S. Okay, I can factor out the y's. I'm going to 1 plus Kp plus Ki over S all over 5S plus 2, which will equal Y of R of S, Kp, Ki over S, 5S plus 2. Well, now what we can do is we can get that expression. Mostly. So it looks something like this. Y of S, Y sub R of S equal Kp plus K sub I over S, 5S plus 2. And 1 plus Kp plus Ki sub I over S, 5S plus 2. And right here, we can go ahead and multiply out top to bottom. Uh, 5S plus 2 and 5S plus 2. For the numerator, it cancels that out. And it cancels this out. mostly. But mind you, that 5s plus 2 is multiplied by that 1, so it does remain in that overall denominator. Which will look something like, let's make some room. All right. Kp plus Ki sub I of s all over 5s plus 2 plus Kp plus K sub I of s. So that's a pretty important expression here. This is, and also, just to further illustrate that this is the h sub c, which is of s, which is the command transfer function. Oh. All right. So now we need to kind of modify this expression further and put the denominator into standard form so we can use it to find the values that we're looking for in this problem. So we're going to multiply the top and bottom by s, and what that'll do is it'll get rid of that s in the denominator of k sub I. We do that. S over s, which what that'll do, that'll transform this into this now. KPS plus KI 5s squared plus 2s plus KPS plus KI. So this is now the h sub c of s expression. Now what can we do with this? Well, we need to further place the denominator into standard form. How do we do that? Well, we have to take the 5 out of that denominator. And by doing that, and I'm just going to show it. See what I did there? I multiplied all the terms of the denominator by 1, but I did that by doing 5 over 5. And recalling that anything, the same thing over the same thing is 1. Infinity over infinity, 1 over 1, 5 over 5, it's 1. So that's allowed. I can do this. So I pull that 5 out. So there we have that. Now, so we place this in the denominator into standard form. Well, what does that allow us? Well, it gives us a means of finding our poles, but we really have, at the moment, we don't have any idea where these poles are. But if we can recall and remember that zeta is also equal to cosine theta. And we can only do this because, so we can use this expression only because our system is stable. And we have a complex conjugate pair. Of poles. So that's why we can use this expression on the left. So we know that zeta is 0.707, which is going to be equal to cosine theta. We take the inverse of that cosine. So it'll be theta will equal the cosine inverse of 0.707. So cosine inverse 0.707 gives us pretty much 45 degrees. Well, that's good to know, 45 degrees. All right. So that's a good place to be. What's another thing that we know that was given? Well, we were given that the time constant was 0.5 seconds. let's recall what the time constant is. Time constant is equal to 1 all over sigma, which is also equal 1 all over zeta omega n sub n. And because this is a stable system and we have a complex conjugate pair of poles, what is that sigma? That sigma, so sigma is the adjacent part of the triangle. Or the distance from the origin to the pole. All right, so let's plug in with 0.5 seconds, which is a half. So tau equals 1/2 equals 1 over sigma, which means that sigma is equal to 2. Now we can plot this on a graph. Let's do that so you can have a visual of what's happening. So this is the imaginary axis. This is the real axis. And all sigma is 2 away from the origin on the stable side. If it wasn't stable, we wouldn't care. It would probably be more closer to infinity. So let's say it's right here, -2. We know that its angle is 45 degrees. So what does an angle of 45 degrees suggest for this triangle? What is special about that? 45 degrees here, it's 45 degrees here. Well, a 45-degree triangle, every side of the triangle is the same length, except the hypotenuse, obviously. But the adjacent and the opposite are the same. So what this is then, this is 2i, this is negative 2i. And then this spot here is negative 2. So this is good because now we can use this information to create a polynomial. So let's create a polynomial using the information that we got from the given values. And this is going to be useful for us when finding Kp and Ki. So the first thing we're going to do is we're going to set this up. S minus negative 2 plus 2i S minus minus 2 minus 2i. And if people are confused about me just randomly writing negative 2 minus 2i, negative 2 plus 2i, the conjugate pair is just, you know, the setup for it, the standard is a plus or minus bi. That's the standard conjugate pair. So I'm going to distribute that negative. Plus 2 minus 2i. S plus 2 minus plus 2i. I'm going to group the S plus 2's together. I don't remember what rule of math says I can do that, but I know I can do that. And now what basically happens is I'm going to FOIL this. And if you FOILed it completely, you'd realize that the middle term would cancel out and you'd be left with S plus 2 squared plus 2 squared. Another way to look at that is just really just S plus 2, S plus 2, plus 4. And I can further FOIL that S plus 2 times S plus 2 out. So we FOIL that out. So I'm going to FOIL this. It'll be S squared plus 2S plus 2S plus 4 and plus 4, which gives me a final polynomial of S squared plus 4S plus 8. Now, we're using only the information that's been given to us, but at this moment, I'm going to call this the guessed polynomial, because the denominator of our transfer function is the real polynomial, but we need to find the values of kp and ki that satisfy well, the guessed polynomial and the actual polynomial. So putting them together, we're going to find out what we need. So got my notes. All right, so for part A, we're now going to compare the those denominators, so those polynomials. That's what we're going to do. I'll write it right here. Comparing poly. So we have s squared plus 2 plus kp plus 5 times s, and then plus k sub I times 5 verse s squared plus 4s plus 8. And we're basically just matching terms. So now, by comparing these, we can set each term equal to its counterpart from the other polynomial, and we can find kp and ki. So let's find kp first. So finding kp. So kp is just going to be 2 plus kp all over 5 times s equal to 4s. Well, that's nice because the s's cancel themselves out. And we're left with 2 plus kp all over 5 equal 4. I can take that 5 over, and we'll have 20. Plus kp equal 20, and then we'll have kp equal to 18. Now we're going to find, so that's part of the answer for A, and we're going to find ki. Ki is equal. Hold up. I'm jumping the gun. K sub I all over 5 will equal 8. And that pretty simply is 40. Because you bring that 5 over, it's 8 times 5, and that's 40. we have those two values. Wunderbar. So that's part A. What's the next part we got to find? Part B is the steady state command error. How do we find that? Thinking about, do I have room on the right side? Oh, I do. Lots of room. So we're looking for part B. Finding the steady state command error for the system. So let's recall that our steady state, well, not steady state, but our command transfer function, control, command, whatever you want to call it, is K sub P times S plus K sub I all over 5S squared plus 2 plus Kp times S plus Ki. And we have to recall our error function because we need the error function to be in agreement with our final value theorem. All right. And again, knowing that H sub C of S is equal to Y, capital Y of S whole over Y sub R of S. Check time. Okay. Gotta keep going. So the first thing we're going to do is we're going to, well, let's also recall the final value theorem. Which just states that as a time constant approaches infinity, I don't know why I don't plug in T, but the professor doesn't. So the limit as it approaches at 0 is S times the error function. So everything I just highlighted in yellow, they're pretty pertinent and important for this part of the problem. And if you don't get it, I don't know, just do this problem 5 more times and you'll get it. So what I'm going to do with this now is I'm going to manipulate the error function to get our E of S for the final value theorem. I'm just going to do that by multiplying the capital Y of S in the expression by 1. But that 1 will just be capital Y of R sub R of S times I am all over capital Y sub R of S. I always call this multiplying by 1, multiplying by nothing. It's basically what you're doing. You see here that this capital Y sub capital Y of S and all over capital Y sub R of S is present here. It's right here. So what we can do is we can back substitute into this expression. And we'll do that, which will give us capital, hold up, better. So capital Y of S minus H, capital H sub C of S times Y sub R of S. Forgot the R there. We can further simplify this into E of S, capital Y sub R of S, 1 minus H sub C of S. Well, that's looking pretty nice. Now, it'll be capital E of S equal, we're assuming that the capital Y sub R of S is a step function, step input. So that's going to be 1 over S in the Laplace domain. And then we're going to have 1 minus KPS plus KI all over 5S squared plus what KP or KP value. What was our KP value? KP value, I'd like to say, let me find it real quick. I'm going to say it's 18. Yes. KP value is 18. Which means that's really going to be 20S. Plus KI, which is 40. Trying to make it a little easier. Okay. And we're going to try to simplify this just a little bit. So let me move everything to the left. Move it to the left. So now, if I multiply the top and bottom by this, well, actually, I jumped the gun again. I got to fix this denominator. So the denominator should be everything as symbolic as possible. Sometimes plugging in numbers as you're doing your math hurt you because you don't get to see what cancels out along the way. You actually make things more complicated if you're constantly plugging in values for your variables. It kind of makes things more messy, and that's kind of weird to hear and to think about, thinking that, okay, if I have, 4 equals B and you're just plugging it in, the higher you go in engineering, physics, it gets harder. So keeping things symbolic is better. So that's what we're going to do. We're going to keep it symbolic. which means I'm going to multiply this inside function, this inside expression, by top and bottom by 5s squared plus s2 plus kp plus ki. 5s squared plus s plus 2 plus kp plus ki. So we're going to do, and what that turns into is E of s equals 1 of s. This is going to be ugly. 5s squared plus s2 plus kp. Save me some time. I'm going to copy and paste this. Copy, paste, minus this. Now you see what's going to happen is because these are the same denominator, I can combine this into one ugly fraction. And that's what I'm going to do right now. And you saw that negative I just got rid of. A negative gets distributed to the kp of s and the ki. And what that does is some things cancel out nicely. Your ki is canceled, and more stuff cancels up as well. Because if you distribute that s, which would just be s2s plus kps, you see that your kps's get canceled out also. So you're left with E of s equals 1 over s 5s squared plus 2s plus, which is 5s squared plus 2s. In the numerator, this would be 5s squared plus s2 plus kp, k sub p, plus k sub I. And there is the transfer function that we have to take the limit of. Well, not the transfer function, the error function. So we do that. We have e as it approaches infinity. Taking the limit as s approaches 0, we'll have s equal all of that. And what happens here is your s's cancel. You plug in 0, and this whole thing equates to 0. That's 0, that's 0, that's 0. So 0 over a number is just 0. Conveniently enough. And let's see, is that what yes. So e as it approaches infinity, for the command. Okay, you're gonna send me the address.
You don't have it?
Did you? Oh, okay. This is just 0. And that is an answer. So I'm going to go ahead and sign off. I'll do the last part later. If you watched this agonizing math, thanks for watching. If not, then cool. So I'm going to sign off.
No. There's address, and I just showed you 275 South to exit 46.